Thank you. Good afternoon, ladies and gentlemen. Right. Firstly, I'm aware of one or two people who are watching this in distant parts, and I realize I need to be a little bit careful with some of the things I say. So hopefully they will be generous with me. Okay. My presentation today covers a period of rapid development in the computer industry. We cover the period from 1946 to 1972, so a long period. But in this period, Manchester University developed 7 major systems, which I think is absolutely amazing, but we'll hear more about that, all of which were commercially available. It is not a detailed technical presentation. There is far too much to cover. Okay, as you'll appreciate, lots of systems and lots of years. Okay, easy questions at the end, but if it's a bit hard, I'll just claim I can't hear because my hearing's not very good. So, okay, right, let's see if I can just work this technology. Be aware I come from Apple land, and it's quite different, but I've got Delwyn here to help me. Right, let's see if we can go to the next slide. Yeah. Okay, right. So 2026 is the 75th anniversary of the shipment of the world's first commercially available computer from the Ferranti factory to the University of Manchester in February the 21st, 1951. So we just missed the anniversary, but we're close. To commemorate this, the idea of this lecture was suggested by Simon Lavington, who I suspect a lot of you are aware of here. Okay, I'll talk a little bit more about him in a minute. It is also linked to the completion of the project to deliver a new display case at TNMOC for the 2 donations made by Simon to the museum. I will refer to this as the case project. And Delwyn and I worked on this very, very hard. It was a lot of work, but please come to the museum and have a look. Okay. Right, now we'll see if I can scroll up. Bear with me. No. Why am I not scrolling up?
Let's try reading that. Like that.
Oh, that's on the bar. On the Apple, you do it in the bar. Here you do. Right. The 2 items that we've got displayed, as you're perhaps aware, are an original Williams Kilburn Tube CRT memory system from the Ferranti Mk1 star, purchased by Avro to develop the Vulcan bomber. Good. And a logic door from the same machine. These 2 items are now together in a case, and they've got lots of words explaining all the history. And in some ways, I'll have to admit, some of the words here are actually taken from that. Okay, right. So now let's see the next bit of technology.
Try the arrow keys, Chris.
Okay. That one.
Oh, other way.
I warned you.
Can get your clicker working again. So down. That slide.
Does it say it wants to stay over there?
Okay. So, no, it's going too far. Okay, this clicker's not working very well.
I know, I did.
Yeah, maybe stick to them.
So that and the left-hand button.
Yeah.
Okay, thank you. Right. Sadly, as some of you are aware, Simon passed away in November last year.
October.
As many of you know, he held posts at the University of Manchester and Exeter. He was the author of 7 books, including 2 which I use extensively in the case project. History of Manchester Computers, which is very readable, a nice top-level summary, and Early British Computers. If you've never seen that, it's an amazing book. The amount of detail in that, the appendices at the back, it is absolutely incredible. Certainly the first of these is out of print, and I don't know about the second one. He was involved in setting up the Computer Science Department Historic Image Collection, HIC. The HIC was used to provide most of the images in this case, the new case, and some of this presentation. It is curated by Jim Miles and his colleague, and it comprises over 3,000 images. Again, highly recommended. Simon was also heavily involved in the Manchester University Library Special Collections, which includes major documents relating to the early major computer developments in Manchester. He was also a major contributor to CCS. And in 2024, he was awarded an honorary fellowship at the TNMOC. He provided major assistance to myself and Delwyn in the case project. His contribution to researching and recording the history of this period in computer development is immense, and I'm sure will be remembered for a long time. Right, we'll see if we can move on to the next slide. Good. Right. You might well ask, why am I doing this? Okay. The original plan was that Simon would put together the material and I would present it as he felt he was unable to travel to London. Then as his health deteriorated, sadly, he asked me to take over. Perhaps my apprenticeship was finished. How did we know each other? Whoops. Bear with me. Okay. Why is it doing that? Okay. Mm-hmm.
Left hand mouse.
Okay. Right. No, it won't move up. I'm not winning, Darwin.
What's the?
I'm just trying to scroll up in there.
Oh, in here. Yeah, just.
It is.
Yeah, just click on it and then.
Have to click on it first. Right. Right, our paths crossed a number of times. The first was unbeknown to me. He was 2 floors above me in Owens Park Student Village. I was on the 14th, he was on the 16th. The second was when he was a supervisor in the electrical engineering degree sessions when I did my degree there. The third, which is an interesting one, was when I came across an entry that I found on the CCS website about CTL, Computer Technology Limited. He referenced a meeting with Ian Barron, who founded the company, where it was stated that there was no successor to Modular 1 as no money was available. As the project manager and system architect for the Momentum Series 8000 successor, I wasn't over happy with that. The fourth was when Simon received his honorary fellowship at the museum. I was the photographer there, as well as being researcher and room guide, I also take photos and make videos. Okay, so we spent some time reminiscing. Our final time together was when he helped me with the research on the case. He contributed enormously to my extensive emails. His emails usually included a chapter from one of his books. Right, we'll see if we can move on. Okay, right, so I'll get there.
It's very slow. Okay.
Right, we'll get to the meat of it now. Scope of this presentation covers from the baby, the test bed for the Williams Kilburn Tube, through to the series of Manchester Ferranti systems onto Atlas and then MU5 and MU6. The slide shows the first operational dates for the systems, with Manchester machines in bold, and also the machines in TNMOC in the same time frame. The image shows the Mk1 logic door containing 12 flip-flops, we believe. It shows an Atlas board in the lady's right hand and an MU5 board, a double 1906A board used on MU5. This image encapsulates the period of this presentation from the Mk1 right to MU5, 1951, 1961, 1971. The pace at Manchester University was relentless. Will the clicker work, do you think, or not? No, I won't bother. Okay. Yeah. Right. The Williams Kilburn Tube was developed from their work in radar systems. They were looking for a faster, all-electronic replacement for the memory delay lines used in EDSAC. It was based on some standard CRTs, similar to those used in radar and television. It was a random access memory system, which the Mercury delay lines are not, okay? The screen is regarded as a grid of dots, where a 1, come on, bear with me, please. Okay. And at each location, you can write a 1 or a 0. In simple terms, the way it works is it changes the electrostatic potential at that location, where if you fire it on full power, it creates a positive area. If you defocus the beam, it takes a neutral area. You then have to refresh that because the charge dissipates. You have to read and restore all the memory, and then you can read it by again pointing the gun. If you want to know more about that, come to the museum and I'll tell you. Okay. In the baby, the CRT capacity was 32 bits by 32. The first successful demonstration of the memory system was in 1947 in November, and it stored 2,048 bits for 4 hours. So they decided that they now got a successful memory system. Okay, I'm just going to try the clicker if I may. Nope. Okay. Is that right? All right, I'm not right in the center of it.
Left hand.
Oh.
Yeah.
Have I missed any now? Sorry, guys. Right. Okay. The system was first patented in the UK in 1946 and in the US in 1947. It may seem as if it was a bit esoteric and academic. It was not. It was used in a variety of commercially available systems throughout the world. The Ferranti Mk1 and Mk1 star, the IBM 701, and we see in the picture an array of, I think it's 24 tubes on the 701, the Univac 1103, and the Russian Strela #1. And that used 43 tubes. I'll get the hang of this one day. I do apologize. Right, yes, I'm sorry. Right. 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 The next thing to be developed was now a test bed for the memory system. They needed a computer to prove that it worked, because their aim was not a memory system, it was working, usable computers, okay? So they worked on the small-scale experimental system, and that was developed in 1948. This is a basic machine, as I said, to test the memory system. Max Newman, who was a major player in Colossus, a bit TNMOC. By now, he was chair of pure mathematics at Manchester and played a major role in the project. The baby successfully ran the world's first computer program on an electronic computer on June the 21st, 1948, on Monday at 11 o'clock. It was largely written by Kilburn. It ran for 52 minutes to calculate the highest factor of 2 to the 18, executing 3.5 million instructions. The smaller image is the listing of the program. It was taken from Jeff Tootill's baby notebook, the notebook that he wrote as he was commissioning the machine. The image is shown by kind permission of the University of Manchester Special Collections. As I'm sure many of you will know, there's a working replica of the baby in the Science Museum, or in Manchester, or the SIM as it's now called. The background shows the slide of the replica system. Now we'll see if we can change slides again. This slide shows the outline specification of the baby. Okay. So 7 instructions, no addition, subtraction and negation only. 3 CRT tubes, 1 for main memory, 1 for the accumulator, and 1 for the current program instruction. The capacity of the RAM was 1K bits. The speed, which is quite remarkable, is over 1,000 instructions per second. The number of valves, as you can see there, 550. Input-output was with key switches, so that 17 instruction program was put in by switches, okay? And you can read the other parameters there as well, okay? The background for the picture is the block diagram, the original block diagram of a baby, again, from Tootill's notebook. And there's a date, if your eyes are good, in the bottom right-hand corner, the 4th of June, 1948. You could see what was in memory because they had a CRT tube, which was a slave from the memory, and so you could read the memory. Okay, right. In 1948, work commenced to extend the baby. Now they wanted to make it into a usable machine. So the purpose was to make it more usable for the maths department, okay, but also the wider university community. One thing to be aware of, you remember at the beginning that I said there was a prodigious rate of development of the machines. It's interesting to know, where did they get the money to do all this from? Because they had lots of computer power and they offered a bureau system, and so they got money in, which fueled the developments. Cunning, okay. One major innovation on this machine was, again, a Manchester first, which was the B lines or index registers. So it made programming of arrays easier. The program, you could actually modify the address within a program to actually step through an array, say, okay? The other thing that is really extremely important there we go, okay, was the addition of the drum. Again, until I started this, I had no idea this was true. I worked on the 6A, which was a page machine, okay? So I was very familiar with paging, okay? Paging really started with the Manchester Mk1, okay? It had a magnetic drum, okay? But it relied on the user to move data backwards and forwards. Can you imagine how difficult that must have been? So in 1906, say, in Atlas, the user wasn't aware. It was virtual memory management, okay? But in this, it was all managed by the user, okay? Right. One of the first tasks of the machine was to run a program to search for the Mersenne primes, okay? This ran error-free for 9 hours. So again, we were getting to see the reliability of the machine, which is important. Though I did read something yesterday that said that one of the Manchester Mk1 stars, there was a big celebration in one of the users that they managed to run it for 2.5 hours without it stopping. So, you know, these were early machines. So to run for 9 hours is pretty good, okay? And it also worked on the Riemann hypothesis, but I won't go through that today. Right, okay. So I believe he's got it. Right. So what were the changes between the Manchester Mk1 and Baby? The word length has increased to 40 bits. Had a lot more instructions now. We've gone to 30 instructions, including hardware addition and multiplication, okay? 2 B lines, okay? 2 CRT tubes, and we've now got paper tape input and output, okay? The important thing, again, to realize is this is not a new machine. If you've ever seen a picture of the original Baby, it fills the room almost, and they added more things on. It's difficult to describe. This room was just a mass of electronics. And clearly the Manchester Mk1 made that even more true. Right, now we moved on. There was an unannounced visit to the Lek-Eng department by the government chief scientist, Sir Ben Lockspizer, okay? He loved what he saw. Don't forget that it was after the war. They were looking for industries to help grow the country, okay? So he initiated a government contract with Ferranti to start production of the machine. This was a 5-year contract, around £55,000 per annum. Okay, and this established the link between the university and industry, which continued for many, many years. And we'll talk more about that later. So following the visit, the grant was put in place. Jeff Tootle was seconded to Ferranti for 4 months to work on the machine. And in 1950, the system was working at Ferranti's Manchester factory. And again, in the background, you can see it's a much tidier machine, and you'll see more pictures later of how that worked, okay? The small image shows the programmer's handbook written by Alan Turing, who by then had also moved up there, okay? So we're getting quite a few Bletchley Park people there now. So what were the changes to the Manchester Mk1 to make the Ferranti Mk1? Okay, 8 B lines. Okay, that was the index registers. Okay, 8 CRT tubes, extended disc drum. Okay, 50 instructions, and we'll see in a minute. That was a few too many. They overshot. Okay, and much faster multiplication. So we now enter a phase in the project, which is I describe as real customers spending real money to do real work. This is a major breakthrough. We cannot underestimate the importance to all of us in this room of what happened then, okay? The green line is the commissioning phase, okay? And the red line shows the acceptance, okay? So you'll see the first delivery was to Manchester University. The second to Toronto. I'll talk in a bit more detail of these in a minute. GCHQ had one, okay? One to Shell, which again, I just recently found out was called Miracle. A lot of these machines were given strange names. MOCOM's Industrial Research Automatic Calculator for Laboratory Engineering, okay? Petrochemicals, okay? So they say, okay? AWRE, Fort Holsted, okay? INAC's an interesting one. INAC, I'll come on to that in a minute. So, and Avros, okay? Right. So, just to remind ourselves, this is why we are here. The first Ferranti Mk1 was delivered February 21st, 1951. The second was to Toronto in 1952. The image shows the Ferranti brochure. We're even into marketing then, okay? So, the Ferranti Mk1 was delivered to Dover Street, okay, which was the Lecenge building when I was there in the 60s, okay? And in fact, just a digression, that time there was no computer science degree. I'm too old to do that, okay? But what was surprising is I was not aware of any of this at all when I was at the university. I suspect, I've talked to many people about this, and it appears that the reason given by many people is they were so busy focusing on the next project. We hadn't got time to tell people what we've done. But in some ways, I'm disappointed that I didn't know about it, but I'm pleased that I can learn about it now. So there you go. Okay, so that you'll see how much tidier the machine is now. It's actually in cabinets, lower and upper, and with a nice display. So yeah, it's it's a proper engineered machine, okay? There was a gentleman called Christopher Strachey, okay? He was a maths teacher originally, but then became an eminent computer scientist. He programmed a machine to play music, but we'll come on to that later. He also wrote it, he programmed it to write love letters. This is the embarrassing bit, okay, because I feel I've got to read this out, okay. How did this work? Well, he had a template. It's a dear, and then a verb, and then you could put some packing words, and then the random number generator would go through the list of sweethearts or the list of adverbs and verbs to write this letter. Darling sweetheart, you are my avid fellow feeling. My affection curiously clings to your passionate wish. My liking yearns for your heart. You are my wistful sympathy, my tender liking. Yours beautifully, Manchester University Computer. I hope you enjoyed that. No, I didn't. Sorry, couldn't say that. Right. Right. The second Mark 1 went to Toronto University for a large discount. This was known as Ferranti, okay? It was used in an extensive range of applications, okay? It was involved in designing the St. Lawrence Seaway, okay? And it was used for industrial, scientific research and software development. So it was a real computer doing real jobs. Right. The Mark 1 wasn't quite right, okay? It had some funny end effects and it left things in registers that it shouldn't really be doing. So after 2 machines, they actually produced the Mark 1 star, okay? Firstly, it was faster than the Mark 1, okay? Much reduced instruction set from 50. You remember I said that was really too many, to 32, okay? It removed these irritations and idiosyncrasies, and it made handling of the backing store much easier. So still they were working on virtual memory, moving towards paging. And again, it was manufactured at Ferranti factory. And the image is the Finnic system. And I can't pronounce Italian, so I'm not going to tell you what INAC stands for. You can look at it, okay? So this is a Mark 1 star at Fort Holstead, okay? So again, you can see how neat and tidy it is, okay? Right. So sadly, as all these machines but one came to the end of their lives, they were scrapped. Okay. The only surviving machine was the Ferranti Mark 1 star at Averroes. At the end of its life, it was donated to Leicester Museum in 1966. And it was when it was delivered to Leicester, there was no room in the museum, okay? So it was stored in what is now the Abbey pumping station, do you think? Is that? Station. Yeah, okay. That one's just been doing a bit more work on this, so sorry. Okay, so it was actually stored in a disused sewerage pumping station, which was also used to restore old fire engines. The console desk, I'm led to believe, was used as a workbench for the fire engine people. It was stored there until 1972. The pictures show the state of the machine in the pumping station. Okay, it was covered in bird poo, and they were in a dreadful state, absolutely dreadful. Okay. So it was stored there until 1972, and then a small team from the Science Museum at Manchester University, including Simon Lamington, discovered it and decided what to do with it. Though I do believe Ferranti were involved in the distribution of the pieces. So where is that machine now? Don't forget, it was just a pile of bits. Okay, the systems are around the world. The largest part, shown here, is in the National Museum's Collection Centre in Edinburgh. And some of you here went to see that last autumn, okay? This, I think, to be fair, this picture makes it look better than it was. I thought it looked rather sad there. And I did say, can I come and help you restore it? But they said, it's all right, sir. The temperature's all right, the humidity's all right. But yeah. Right, so where are the other pieces? Okay, well, we've obviously got a section of that, a logic door from it in TNMOC. There's one at the Science and Industry Museum in Manchester. There's one in the Manchester University Computer Science Collection in the Kilburn building. There's one in the Computer History Museum in Mountain View in California. And there's one in the Smithsonian Museum. Just a little diversion. I think I've got time for this. Right. I read somewhere that there was one in Smithsonian, but I wasn't sure. Okay. So I went to my computer and, you know, when you do a Google search, it comes up with an AI summary. So I said, is there a portion in Smithsonian? No, there isn't. I wouldn't accept that as an answer. Do you want to dive deeper? Yes, I do. Yes, there is. Make up your mind. Okay. So much for AI, but there you go. Okay. So there is a portion, and yes, we've got pictures of it in Smithsonian. Whether they know what it is, I don't know, but still. Okay, right. So that's where the pieces are. So we have got a reasonable legacy of this first major phase of computing. Okay, so yes, we've recovered the situation from nothing. Right. So the NRDC grant started the collaboration between the university and originally Ferranti, and then when Ferranti's commercial side became ICT and ICL. So the 7 systems were developed, okay? We know about the Ferranti Mk1 and the Mk1 Star. There was then the Manchester transistorized computer, the first transistor computer in the world, which went into production as the Metropolitan Vickers machine. So they became a player. Again, I had no idea this was true until I found this. But surprisingly, there were 6 or 7 machines, but they were all used internally. Okay, Meg, or the megacycle machine, because they wanted to start and go faster now. They'd got better technology with transistors. Now they want to go faster. So this was a much faster machine, and this went into production as the Ferranti Mercury. Atlas, okay, I used that as a student briefly, and then finally MU5. I'll talk a bit more about the detail of those in a minute, okay? After these machines, MU6 was then developed, which was a series of high-performance specialized processors and was regarded really as the end of an era of large system development at Manchester University. Right, so I've talked about the first 2 of those, the Manchester from Ferranti machines. Let's go into a little bit more detail about the rest. Right, the transistorized computers, because don't forget, up until now, we've used valves. Okay, and you know, valves produce big hot machines. If you come to the museum and seen Colossus and Edsac, you know, literally thousands of valves generate using 11 to 15 kilowatts of power. Okay, so the first version of the transistorized machine was in 53. Okay, that was point contact transistors for the electronics people here. So 92 transistors and 52 diodes. Okay, there was a second version in 55. And then there was the final version, the Metropolitan Vickers version, operational in 56. And this used junction transistors. Okay. This surprised me. Similar to the Mk1, but using only fast drum for memory. Don't quite understand that. So I actually don't know the relative performance of it, but right. In 51, okay. Wait a minute, what's going on? It moved on then. That's all right. Bear with me. Okay, right. So the production version of Mega was made by Ferranti. Okay, it used magnetic core. Right. Some of you may know that was developed at MIT in 1951 out of Project Whirlwind, and obviously core was a significant development. Certainly in my experience, they were in production for used in machines for about 15 years. Okay, highly reliable, highly robust, still used in space systems. Okay, the Apollo missions used core memory. Okay, and I believe even SpaceX. I don't know about Artemis, but you know, they're still using core memories because they're not influenced by alpha, beta, and gamma rays out in space. So long as you avoid magnetic storms, you're okay. Right. Okay. First Mercury was delivered in 1957. Okay. And Manchester then took delivery of one of these in 58. Okay. Now we're starting to shift development a little bit more towards software, because software development up to that time was really rather difficult. If you look at some of the papers and things, the coding systems, the instruction set, your own virtual memory system. So we're starting to look at improving this. So really one of the first autocode systems, which is a slightly higher level of programming, getting more and more of an assembler. Okay. And 19 of the Mercury systems were sold. Don't do that to me. It was all going so well. Blimey. Right. Right. We're nearly getting to the end. Okay. So Atlas. Okay. A high performance system, and clearly the systems are getting more complicated, more complex, more sophisticated. They're taking longer to develop. Okay. So this was from 56 to 62. Okay. Joint development with, well, it says Ferranti, but I don't know whether it was ICT by then, because certainly when I joined ICL in 67, a lot of the 6A team was still down at the university, and then they migrated back to work on the 6A. So first production in 1962, and for a short time, it was deemed to be the world's most powerful computer, a supercomputer. Don't know actually how long, but you know, by then the Americans were powering along as well, as you would expect. Okay, again, strong emphasis on software. It's all going wrong again. Okay. So again, second generation of autocode to again make it more programmable, okay? We've now got multi-programming. Don't forget, as I say at the museum, the computer you've got in your pocket's perhaps got 10 cores, okay? All these machines, all these mainframes were single core. You know, I ask people at the museum, how many core do you think the 2966 has got? 10, 20, 1. I say it's all done by smoke and mirrors, okay? So it's multi-programming. And so you need the kernel and the operating system to manage all that, to make one program is allocated the correct memory, it doesn't write over somebody else's program, etc. You know about these things, okay? And high-level languages, okay? We've moved up even from autocodes now, particularly Algol 60 and Fortran, okay? 6 Atlas 1 and 2 computers were delivered from 62 to 66. So Manchester University, okay? The National Institute for Research in Nuclear Science, okay? London University, okay? Then we had the Atlas 2. And again, I don't know why, maybe somebody here might know, the Atlas 2 didn't have paging, okay? They went backwards. Well, in my view, okay? And they were, the machines there were Cambridge, okay? And Titan machine, Aldermaston, and the Cambridge CAD system. Right, I need to be careful what I say now. Don't I, Roland? Okay, who is watching? Okay, right. So work started on this in 1966. It was aimed to be 20 times faster than Atlas. Again, major steps in performance, okay? It was asynchronous, as was Atlas and the 1906 ANS, okay? The technology, which is shown here, a multi-layer board, a little bit about the multi-layer boards, as we're doing all right for time. The multi-layer boards were an ICL innovation. The technology used in MU5 and 6A was emitter-coupled logic, high-speed logic, okay, very fast rise and fall times. So you had to use transmission lines with a matched impedance to ensure you got clean signals, okay? So these multi-layer boards, they had layers so that, in fact, the logic layers were within earth planes and you could guarantee the impedance of the lines, okay? The top yellow image is a double layer, double size 6A modules. All the 6A modules were half that. The MU5 was double that. It had multiple arithmetic units. The instruction set was optimized for higher level languages, okay? So we moved on a step further now, not only using high level languages, but saying now we want to make the machines more efficient at running high level languages, okay? So I believe that this architecture was particularly aimed at Algol and Fortran. One can surmise that's because Algol was a general purpose language and Fortran was more for scientific use, okay? So they're trying to cover the range of applications, okay? We're working to improve the efficiency of the supervisor. And again, we know from ICL, the considerable amount of work went into what they call executives and now called kernels and operating systems, okay? The operating system for this machine was MUSS, okay? And it used the 1905E in its development. So that was a fairly big top-end ICL machine, and it was used for providing the peripheral input-output, and it was a test bed for an associative store, okay? And again, I'm not sure whether this was a Manchester innovation or not, but they were starting to use, instead of addressing store by the address, but by the contents of what you wanted to address, okay? And we've recently got delivery of a 3900 at the museum, which Delwyn is going to try and get working. And again, I was surprised that's got a content addressable store, CAFs. So again, as I say, I don't know whether that started at Manchester or not, but what happened to MU5? It really fed it into the 2900 series. Okay, so that was the last of the dedicated hardware machines. Okay, so this machine is when this graph is when AI had a good day. I asked AI to plot this for me, and it kindly did this, and it's not bad. Okay. So I'll let you pause for a minute and look at that. Okay. So, but let's make it a little bit easier. I did this, not AI. Okay. It's a log-lin graph. So even though it doesn't look very spectacular, obviously, you know, it's quite a steep exponential curve. Okay. So, as we discussed earlier, the Ferranti Mk1 was delivered in 1951. Okay. The machine was programmed by Christopher Strachey not only to do love letters, but to play music. So that if those who are able would like to stand. No, maybe not.
Lift, Jim. Another tune coming up.
Yeah, it's better. I don't know.
Another one coming up. Keep on cutting.
Okay, what on earth was that? That was, okay, a recording that was a children's BBC program, outside broadcast from the university in February 21st, 75 years ago. Okay, no, sorry, that wasn't the date. It was November. Okay, mistaken. Okay, so you know, computers were getting clever now. They could play music and okay. So that recording, well, that's a tidied up version. The first one is really very scratchy. I'd help with people from the university and Chris Burton to find that. It's now recognized as the oldest known recording of computer music. No. Right. Just check I've done that right. Didn't miss one. No. Yes. Right. So we've come to the end of the journey. Okay. And as I said, it covers an awful lot of ground. Okay. A lot of people helped me with this. Simon Lavington, just an immense help at the beginning. Jim Miles, who's pictured there standing in front of a large picture of a Manchester Mk1. He looks after the HIC collection. James Peters, who looks after the special collection from the University Library, and a couple of guides from the baby team. And just to be correct, I must recognise that obviously all the pictures we use, I had to gain permissions both from university for the image and also for the originator of the image. Okay, so those are the people who, and it's just worth saying that the two-till notebook was interesting because the university could let me use the image, okay, but the rights for it were still held by Tootle and his family. So with the help of Chris Burton, I then was directed to America, first to one of his sons and then the two other sons, so that I got permission from all three sons to show it. We had to be correct with all this because my director wanted a spreadsheet of the permissions of everything we did. Right, I finished. Thank you very much, ladies and gentlemen.
To the ceiling lights. Yeah. I think there's some of those on the radio some years ago. I know, but it's heavy for me. This program I learned. What's code? Just one corner from here. Is that an English electric? ICL. Sort of test better than research. Thank you, Chris.
No, it's not PowerPoint, it's Microsoft. I love Apple. No, it's just me. Yeah, thank you.
Questions? Yes. It was just a fascinating talk and wonderful slides. I commend you on the wonderful slides. But just a couple of questions. First one was, I forgot which machine it was, but you discarded some instructions were discarded from 50 to 32. Wonder what sort of instructions they were. And secondly, I was a bit puzzled about the program that the baby was running, finding the highest factor of 2 to the 18.
All factors up to
Understand that all the factors are obviously powers of 2, and I would have thought the highest factor of 2 to the 17, which wouldn't have needed 3.5 million instructions to find that out. But I misunderstood something. Why the number of instructions that you discarded, what were they? And
I'll have to admit that taking the second one first, I haven't studied it. I mean, I've got the listing, but I'm afraid with everything else, I haven't actually looked at it. But if you go online, you will easily be able to find the listing, and then you'll be able to work out for yourself. I'm sorry, that's not a very good answer, but I really haven't. An answer to the first, I'm afraid, I don't know that either. No, I won't hazard a guess. I don't know whether. No, my colleague dealt with it. No, we don't know. I'm sure we could find out again, but I'm sorry, I can't answer that.
I can probably answer the first one. Yes, the answer is 2 to the 17. It wasn't, the program obviously wasn't done to find something that was unknown. It was done because it took a lot of instructions to actually divide 2 to the 18 by every number to see I did and what didn't.
You know what the answer is.
The answer is so, yes, it took a lot of instructions to do it, and the point was it was a program to exercise the machine.
Thank you.
It's an observation rather than a question. Thank you very much indeed. It was fascinating. I was involved with the MU5.
Yes, okay. Well, bring it up.
No,
I'll come down.
I
was thinking of doing my coffee
quite-
at 3:30,
Can you hear me?
and then I've just thought, okay, I've
I
been
just need to mute his mic when he's talking. Sorry, shall we come forward a bit and shout?
You mute people online.
Oh, no, it's okay.
There you have. Carry on, Jim.
Right, sorry. MU5 between the years of 70 to 75. I had been working for Ferranti, then got turned into ICT, then left. But I was working at the university with Tom Kilburn and Simon and all the Manchester team before I left. Came back in 1969 to help set up the regional centre, which was hoping to install a 1906A and a MU5 because the British government wanted us to buy British for this supercomputer centre to be shared, a regional centre at Manchester. Unfortunately, they couldn't make it work on time, the MU5. So we ended up with a good British compromise of a 1906A at the front with the CDC 7600 at the back. And that was commissioned in West Gorton. So you probably came across it in your...
I was involved in the link between the two. I went to the States.
You were on the project.
Yeah.
Scars as well. Okay, right.
But I also, the front end of that, there was 3 machines in the chain. There was actually a front end processor, which was actually a CTL modular 1.
Yes, yeah, absolutely. Well, I was trying to run a computing service on that, which was quite a nightmare. I had a 6A in the Manchester building, which became the Kilburn building. I had a 1905 in the UMass building. I had the 7600 in West Gorton running. It was, and I inherited Atlas as well. So I was running a service on Atlas. So that was quite, but the point about the MU5 was we were trying to buy British because I, was supporting the government policy, even though we had to get the best solution for the university. And in fact, because the MU5 was late, they couldn't make it fast enough. ICL were also trying to make the 1908, which was going to be one up from the 6, and they couldn't make that fast enough. So the compromise was a 6A front end of quite a lot of money with the 7600 at the back end. And that actually impacted on the development of the MU5 because attention was taken away to service the university's project. And there was a bit of a falling out over all of this, which you probably were being sensitive about when you spoke.
I'd left by then.
I think at one point, ICL by then, and the university were at loggerheads and there were little writs flying over all sorts of reasons. They came back together again in the end. And as you say, the MU5 eventually was a major element in the design for the new range. But that was an interesting period.
Well, interesting. Well,
it was hard work getting that project with 6A 7600 to work. We did.
Going back to the 8, as I understanding, but I was a young graduate there, so perhaps we got the myths rather than the facts. Any of you know that the 6A, it was water cooled. It used 8 gallons of water a minute in pipes that big. And they reckoned that in order to build an 8 or 8A, they would have to divert the River Irwell to the factory to provide enough water to cover the commissioning floor. Well, not literally cover it.
And that's another little aside. The Manchester University had a 10,000 square foot room ready for this supercomputer complex. And underneath was a 6-foot void because of coping with all those pipes that we were half expecting. Never got used, but it did get flooded once.
Yeah. Thank you very much. Yeah.
Questions online?
Brian Russell has got two.
Just a second, Robert.
He says need to be corrected. I don't know, Brian, do you want to unmute and talk about it? Or I can just read them out from the comments.
I need to read them.
Okay.
Brian, not correct.
I saw it out the chat.
One of Brian's myth corrections was apparently the SSEM, he says, has 567 valves, not when he counted in 2018, he came up with a slightly different number from looking at logic diagrams and from the physical replica. And his second myth was the SSEM run of the highest factor program of 2 to the 18 was actually on the 22nd of June. On the 21st of June, they ran smaller numbers like 31 and 19, and then some larger numbers, he says.
Ooh.
I don't know where these facts are from, but he seems very sure of it.
Yeah, because I mean the 21st is in Simon's books, and that's interesting. Okay.
It's a big debate about a precise date.
Yeah. Let's say June.
Can I say two things, Chris? The highest factor program was chosen because the same program would run for different lengths of time according to the starting number. So the program, it was the same program would have run on the 21st and 22nd. It's just that on the 21st, they put in a relatively small number so that it would work within a reasonable time, and testing it further on the following day by putting in a bigger number. But the same program could be made to run for however long you want, depending on the starting number. The other fact I'd like to mention is when we were running MU5, we had a visit from people at Livermore. And they found that MU5 took about twice as long to run their workload as the 7600. But the 7600 took 30 times as long to compile the program because they had to do an awful lot of optimization. The MU5 compiler didn't need to do any optimization because the instruction set was conducive to good code churned out by Algol and Fortran compilers. So in that sense, the MU5 was successful. The other thing about associative memory was that the paging registers on Atlas were associative. So what was new in MU5 was that we did it at a single word level inside the processor. So instead of having registers, there was a small associative store that acted as if it was a set of registers, but the programmer didn't need to know about it. It was all taken care of automatically. In fact, in the hardware.
Thank you. Your point about the compiler, I think, came up in our recent talk about compilers. So, yes.
Yep.
Questions in the room? Yes.
Whatever happened to the Ferranti Orion and Nebula? In the early 1960s, I had a job working for the Prudential Assurance Company Limited, who were very proud that they were ordering a British computer. Obviously, they were ordering it from the drawing boards, and in particular, its programming language was also being created from the drawing boards. As a potential programmer, I was dealing with their old gold sheets when they decided that one particular instruction didn't work the way we thought that it was going to work. So it was quite frustrating. And I left in 1964. So does anybody know about Ferranti, Orion, and Nebula?
Could you hear that question online? Was the question audible?
Yes, I can hear it.
Okay, fine.
I can tell you that there are at least parts of a Ferranti Orion in storage at Birmingham Science Museum. I've seen the control console for it. I don't know about the whole thing. I'm afraid I don't know anything about Nebula though.
Just as an aside, I remember Harold Gearing, who was one of the founder members of CCS, mentioning that he still drove a Ford Orion because Metal Box had a Ferranti Orion when he ordered it for them.
Even means car, means computer.
There's been a little bit of debate online about whether, or to what extent, Bletchley Park contributed to the developments in computing at Manchester. I don't know whether you want to talk about that at all, Chris. So obviously,
The individuals.
Well, you had Max Newman there. You had Alan Turing later, obviously, as well. Both Bletchley Park. Jack Good, I believe, was from Bletchley Park.
Okay, I'm only aware of what I said, which was Newman and Turing. So,
When they were in Manchester.
yes, yes. You know anybody else?
Well, George, who I've maybe one of the baby volunteers. I don't know if you want to say anything about this, George. Still here?
Yes.
He's not up there.
Speak. Speak.
George says he doesn't speak.
Yes, I see.
Dan, did you want to?
If I remember rightly, I.J. Good came from Bletchley Park to Manchester.
Kind of forget about Turing and Manchester is that he arrived at Manchester with a working machine. So he could start to use the machine rather than spending time designing it. And this led to various things that he produced, particularly work on the mathematics of plants and
Exactly.
so on. If you read the book on computing at NPL, you read between the lines, the best thing Turing ever did for pilot ace was to go to Manchester, because they stopped the worry about precision, word length, all the really intellectual things, and could get down with soldering some bits together and see if it would work.
Yes, in fact, just doing a little bit of a plug, there is a new pop-up exhibition at the NMOC, which talks about the work that Turing did to do with nature, finding the patterns of plants, of fir cone, fishes, and all these things. So yes, that was an interesting move for what he was doing.
Right, for the wrong reason. George just pointed out there was a report from Jack Good where he talks about instructions for the baby.
I mean, I think what we're demonstrating is there is so much information out there, but it's quite difficult to pull together. And sometimes you see something in passing when you're looking for something else, and then you go back and try and pick up that thread. Certainly, I'll have to admit, is the first time I've ever done anything like this, and I really did find at times I was just overwhelmed with information. And I can't in any way claim that I've covered these topics in depth. As I said right at the beginning, it's an overview, okay? Each of those machines really could justify a lecture in their own, I'm sure. But, I wanted to paint the picture.
Which I think you have. Any further questions?
I think maybe just a little musing on Turing. As we said, Turing only arrived at Manchester after the machine was working. And his main contribution there was to write the programming for the machine. First edition of it, which you showed in your talk. And it was widely held at the time to be almost incomprehensible by people who tried to program using it, because the program the machine used 32 instructions were 32. There were 32, so 5 bits for instructions, but the terminology that Turing used was the teleprinter code for these 32 characters, and they weren't even in order, and a lot of them were strange symbols. So the prerequisite was you actually had to learn off by heart these 32 symbols in order to understand the manual at all. And it apparently also contained a lot of mistakes. So by the time you'd gone through the manual and found all the mistakes and corrected them, then you actually might know how to program it. And of course, it was revised in a subsequent edition to make it slightly easier. I think that's quite amusing based on Turing is found at the ACE for producing a machine that was almost impossible for people to program.
But he continued in that.
Which didn't bother him. It's bothered everyone else.
But it's interesting. Yes, I skimmed through some of that handbook when I went to look at the special collections. You can actually look at any of these books if you want to read that. If you want to look at the Two Tools handbook, you can go up there and touch and look and take pictures of these. Okay, it's quite awesome, really. But the programmer's handbook starts off with how a human tackles working out a problem. So he starts right at the beginning of a thought process and then develops that on to how a computer would do it and compares a computer to a human being. And it's, yes, I only skimmed it, but it's fascinating.
There is a question online. David Renshaw has his hand up.
Yes, Chris, I know you worked on George 4 at one time. This is taking the discussion a few years further forward. But the difference, for the benefit of the hardware people, is that George 4 was a paged executive for the 1900 series, the large 1900s. And we had the similar situation of Atlas 1 versus Atlas 2, where the main difference was that Atlas 2 didn't have paging. And I wondered whether we had any figures as to showing the benefit of paging as opposed to the unpaged equivalent.
That could be a lecture in its own right, I'm sure, because I'm biased, but I found the 6A a fascinating machine. All right, it was the first machine I've ever worked on, but it was essentially my description of it's a fusion of Atlas and the 1900. Essentially, it was molding the Atlas ideas to be a straightforward, compatible 1900 machine. Yes, and the work that I did, as you rightly say, to make a George 3 exec running George 4 was just entirely to do with the supporting paging. But no, I left really as the machine was entering production, so I haven't followed the development through. In fact, I've tried to find out a lot of the details of how a 6A works, and I really find it very difficult. I've still been in touch with Malcolm Kershaw, the original project manager, my team leader in Korea, and I've wanted some manuals, detail engineering manuals on a 6A. And there's nothing again. It's really a little bit like the Manchester machines. Trying to find information is so frustrating. In fact, if I just might give a plug, okay. I mentioned in passing my work at CTL, okay. I was a system architecture for the replacement machine. I've lost contact with all the people who worked with me, and also I've no detailed documentation about it. I would love if there's anybody out there who can tell me the detail of how it works. All I know is the idea that I came up with: you distribute the operating system throughout the machine, okay? And so we cut up the executive, then the operating system spread it. And so there was significant intelligence in all the peripheral controllers, but I can't remember it. And I'd love to find out about it, because I think I was asked by Dick, I think, to write an article for Resurrection. I just haven't got enough information at the moment.
Yeah. As far as the Atlas is concerned, the motive, I think, for creating an unpaged one was that the whole machine was cheaper, and because of the absence of all the paging hardware. And whether that was important would be determined by what sort of workload you had. If you had hundreds of students logged in online, then obviously paging would be some benefit. But if you were the sort of user who did major number crunching with very few programs in the machine, you probably wouldn't get any benefit from paging.
Just an aside, David, you're not the David who was a test program on the 6A project, were you?
Yes, the very one.
Oh, do you remember me? I remember you.
Yes, you were the designer of the peripheral processor, weren't you?
Well, one of many. Sorry to
have a drink afterwards.
Yes. Just as a matter of slight passing interest, you mentioned the contents of the professional file store. Longer-standing members of this society remember about 20 years ago, Amos Carmichael and myself
gave a presentation on the use of CAT in the ICL product. Its use around the world in police forces, defence matters, and all sorts of things. I, for instance, put it into Botswana police as an investigative device.
Yes, I want to learn more about that.
Yes, everything was wrapped up.
I think I can probably blame MU5 then for terminating my career at ICL. I just realised what you were saying. I joined ICL in 1969, and I was put on to one of the teams specifying the architecture for the new range. And I worked with John Iliff on the basic machine architecture, and that got whopped by something else, and presumably that was the MU5. So thank you, MU5. I then left ICL and went elsewhere.
I'm sorry.
You had a successful career. Well, yes, thank you very much. Despite all the challenges, presentation, it was a really interesting presentation. I think we all learned a lot. So
I hope so.
Ladies and gentlemen, our next meeting will be on Thursday, the 21st of May, as usual. Mr. Dermot Turing will be speaking about misread signals, how history overlooked women code breakers. And if you may remember, I think this will be particularly interesting given the presentation we had last March, so it's over a year ago, at the code breakers from Newnham College, Cambridge, who were drafted into Bletchley Park. At least one of those searches on that is coming because I've alerted. So thank you for coming. Hope you've enjoyed it. We'll see you next month.
Chris, just before you sign off, could you just comment, we might have the virtual for next meeting. There is still scheduled to be a tube strike that day.
We'll let you know.
The commission meeting as well.
Union will let you know.